Good morning, one and all. My name is V. Abhijit Kumar. My roll number is 249518660. I am studying in third semester CSE, AI and ML, that is Computer Science and Engineering, with the specification of Artificial Intelligence and Machine Learning, Institute of Aeronautical Engineering. In this video of the complex engineering problem CEP of the subject of logic programming for artificial intelligence, I am going to explain about the topic animal classification from images. Let's go through the contents. In the first place, I'm going to introduce the topic. What is animal classification from images? And after that, I'll explain about image classification models for animals. Then I'll explain logic programming fundamentals in AI. Then I'll explain integrating logic integrating logic programming with image classification. Then I'll explain a case study, YOLO and GPT-4 vision for animal identification. Then I'll explain challenges in animal image classification. Then I'll explain applications in ecology and conservation. Then I'll explain future directions, neurosymbolic AI and hybrid models. Then after that I'll summarize the topic, and finally I'll conclude the topic. Introduction. What is animal classification from images? Animal classification from images is the process of automatically assigning labels to the photographs based on the species or categories of animals present in the image. This represents a fundamental task in computer vision and artificial intelligence, and transformative applications across wildlife monitoring, ecological research, and advanced AI systems. The technique combines sophisticated image processing algorithms, pattern recognition, technologies, and intelligent reasoning capabilities to enable automated analysis of vast image datasets collected from camera traps, aerial drones, satellite imagery, and citizen science initiatives. Basically, three steps we have here: image processing, pattern recognition, and AI reasoning. Now let's go through image classification models for animals. Modern animal classification relies on powerful deep learning architectures that have re revolutionized computer vision capabilities. These sophisticated models can process images with re reasonable and remarkable accuracy, detecting subtle features and patterns that distinguish different species. First model is YOLO V8. It is a real-time object detection model which achieves 98.7% of accuracy on wildlife species classification tasks with exceptional speed. ResNet 50. It deep residual networks excelling at fine-grained species differentiation through hierarchical learning. Vision Transformer. It is an attention-based architecture which captures global image context for super classification performance. And finally, EfficientNet. It is an optimized neural architecture which balances accuracy and computational efficiency for scalable deployment. Transfer Learning Language, or TLA. Pre-trained models enable rapid development by leveraging knowledge from millions of images, requiring minimal additional training for new animal classification tasks. Zero-shot classification. Advanced models like Meta CLIP and AIT CLIP can identify previously unseen species without retraining. dramatically expanding classification capabilities. Now let's go through logic programming fundamentals in AI. Logic programming represents a declarative paradigm that uses formal mathematical logic to encode knowledge and enable automated reasoning. Unlike traditional procedural programming, logic programming focuses on describing what relationships exist rather than how to compute them. Basically, here three major aspects we have to discuss. One is rule-based inference. Systems derive new facts from existing knowledge through logical deduction, enabling intelligent reasoning about animal characteristics and relationships. Symbolic reasoning. Prolog and similar languages manipulate symbols representing real-world entities, allowing explicit representation of domain expertise. Knowledge representation. Formal structures encode taxonomies, habitat constraints, behavioral patterns, and anatomical features of different animal species. Basically, logic programming provides the foundation for explainable AI, enabling systems to justify their classification through transparent reasoning chains that domain experts can verify and understand. Now let's go through integrating logic programming with image classification. The hybrid approach combining neural networks with logic programming creates powerful AI systems leverage the leverage the strength of both paradigms. Neural networks excel at pattern recognition from raw visual data. What logic programming provides structural reasoning and domain knowledge integration. Basically, here four steps. Image input. Raw visual data from camera or sensors. Neur Neural classification. That input is classified. Deep learning models extract features and predict species from that image. And after that, logic verification. Logics are verified in that image. That means rules validate predictions in and against domain constraints. And finally, refined output can be occurred. Enhanced accuracy with explainable reasoning. Example application. Logic rules can verify that a predicted polar bear classification is consistent with the image's geographic metadata, Arctic regions, time of year, and visible habitat features, flagging inconsistencies for review. Now let's go through a case study. YOLO and GPT-4 vision for animal identification. The challenge is that wildlife organizations process millions of camera trap images annually, facing high computational costs and false positive rates that waste valuable research time and resources. The solution we have is a two-stage pipeline which combines YOLO V8's efficient detection with GPT-4's vision, sophisticated sophisticated reasoning capabilities of the vision, creating a cost-effective and accurate classification system. Now, in this case study, step 1 is filtering. YOLO V8 rapidly scans images to detect animal presence, is eliminating empty frames and reducing dataset by 60% to 70%. Stage 2 is classification. GPT-4 analyzes remaining images, identifying species with contextual understanding. And finally, stage 3, lot verification. Logic rules validate classifications against ecological knowledge, catching errors like elephants in non-native habitats. Here, 85% of cost reduction can happen for our benefit compared to the processing all images with advanced models, 94% of accuracy rate on complex multi-species identification tasks, and 10x speed improvement processing throughout versus manual classifications. Now let's talk about challenges in animal image classification. Despite remarkable advances, animal classification systems face persistent challenges that require ongoing research and innovative solutions. Understanding these limitations is crucial for developing robust and reliable AI systems. There are four aspects which we have to discuss. Environmental variability. Changes in lighting conditions, weather, seasons, and camera angles create enormous variation in how the same species appears across different images, challenging model generalization. Occlusion and pose variation. Animals frequently appear partially hidden behind vegetation, in unusual positions, or at extreme angles, obscuring diagnostic features that models rely upon for identification. Class imbalance. Common species dominate datasets with thousands of examples, whilst rare or endangered species may have fewer than 50 images, leading to biased models that perform poorly on conservation priorities. And finally, ambiguous classifications. Juvenile animals, distant subjects, similar looking species, and poor image quality create scenarios where even report biologists struggle to make definitive identifications. Hence, these are the challenges in animal image classification. Now, let's go through applications in ecology and conservation. Animal classification systems are transforming ecological research and conservation efforts worldwide, providing unprecedented capabilities for monitoring biodiversity and protecting endangered species at scale. There are four applications which we have to discuss. Population monitoring. Automated systems track wildlife populations across vast territories, detecting trends and threats in real time without disturbing natural behaviors. Migration studies. Classification systems identify species along migration routes, revealing critical habits and timing patterns essential for conservation planning. Anti-poaching efforts. Real-time detection alerts rangers to endangered species locations, enabling rapid response to potential poaching activities. Citizen science. Mobile applications democratize species identification, enabling millions of nature enthusiasts to contribute valuable biodiversity observations. Now, before before concluding the topic, I would like to explain about the future directions of this. The convergence of neural perception and symbolic reason heralds a new era, a very new era in AI, where systems combine the pattern recognition process of deep learning with the interpretability and domain knowledge integration of logic programming. Basically, five directions we have to discuss. Neuro-symbolic AI, deeper integration of neural and symbolic approaches. Global impact, scalable solutions for worldwide conservation efforts. Few shot learning, classification of rare species from minimal examples. Edge computing, real time on device classification in remote locations. Explainable AI, logic programming enhances interpretability. System interpretability. Now let's go through the conclusion. Hence, animal classification from images represents a powerful synthesis of computer vision and logic programming, demonstrating how a hybrid AI approaches can address real-world challenges by combining the perceptual capabilities of neural networks with the reasoning strengths of symbolic systems. We create more accurate, explainable, and trustworthy AI solutions. These advances promise transformative impact for ecological research, conservation biology, and the broader field of artificial intelligence, paving the way for smarter systems that truly understand and reason about the natural world. And now finally, I would like to thank the respected professor for giving me this wonderful opportunity to speak upon this wonderful topic. Thank you.